29th September 1957, Chelyabinsk 40, a closed city that officially did not exist on any public map. In the waste storage canyon of the Mayak Production Association, a routine Sunday shift continues, log pages stamped, instruments at rest, cooling water flowing through manifolds as it had for years. At 16 hours, 22 minutes local time, operators feel a vibration, then a pressure front strong enough to rattle windows 300 meters away. Perimeter dose rate monitors, which had shown near background levels all morning, suddenly climbed to values that trigger internal emergency thresholds. Within minutes, a column of smoke and dust rises to approximately 1 kilometer, flickering with an orange-red light as it settles on buildings, equipment, and people. Later reconstructions will estimate that about 740 petabecquerels, 20 million curies, of fission products were released from a single buried tank. Around 270,000 residents live under the eventual path of the fallout. From this moment on, every dose estimate, evacuation list, and epidemiological study would revolve around one number: 20 million curies released from a single failed cooling system. A classified decree on a Moscow desk assigns a mountainous region of the southern Urals to the Ministry of Medium Machine Building. The year is 1945, the war has just ended, and the strategic calculus is clear. The United States has demonstrated nuclear weapons. The Soviet Union must match that capability as quickly as possible. Within a few years, that single administrative decision produces 6 plutonium production reactors and a radiochemical reprocessing plant, collectively known only through a postal code, Chelyabinsk 40. The facility itself is sited near the town of Ozyorsk, a location that will remain absent from public maps for decades. The plant's formal designation is the Mayak Production Association, though Mayak means lighthouse, a name chosen for its neutrality, revealing nothing about the work inside. The Ministry of Medium Machine Building, Minzredmash, operates as the lead body overseeing all Soviet nuclear weapons production. Mayak is one of its flagship installations. The plant's mission is to produce weapons-grade plutonium through a complete fuel cycle. Natural uranium fuel enters graphite-moderated, water-cooled production reactors. Spent fuel moves to the radiochemical plant. Plutonium is extracted via the sodium uranyl acetate process, and high-level waste is disposed of, initially into the Teka River, later into underground storage tanks. The process is straightforward on paper. In practice, it generates enormous quantities of radioactive waste with decay heat that must be continuously removed. The strategic aim is clear: match the US stockpile quickly. Planners assume that waste can be handled temporarily via local water bodies and interim storage until better systems are developed. In practice, basic environmental and occupational safeguards lag far behind production targets. One historical review notes that 17,000 Mayak workers received radiation overdoses between 1948 and 1958, a figure that underscores the human cost of the rapid build-up. The Soviet industrial safety framework formally required strict observance of technological regulations, but real oversight was delegated to plant management, who operated under intense pressure to meet production quotas. The drive for rapid weapons output hard codes a bias toward throughput over redundancy. That institutional design, more than any single component, increases the probability that a failed cooling system will remain unrepaired. By 1949, Mayak delivers its first plutonium cores. The same documents that celebrate that success already record worker doses in grey, but almost nothing about long-term waste heat management. In a later memo to the CPSU Central Committee, Minister E.P. Slavsky will write that the culprits committed a gross violation of the technological regulations for the operation of storage of radioactive solutions. That phrase, gross violation, will become the official shorthand for what was, in reality, a structural blind spot in how Mayak measured waste behavior. Between 1949 and 1956, Mayak discharges approximately 7.6 times 10 to the 16th to 10 to the 17th becquerels of radionuclides into the Teka River, including about 1.2 times 10 to the 16th becquerels of strontium, 90 and 1.3 times 10 to the 16th becquerels of cesium-137. The Teca flows through rural districts downstream of the plant, serving as the main source of drinking and washing water for dozens of villages. A dosimetrist's field notebook records rising beta counts along the Teca shoreline, while children still fetch water from the same river. Management treats the river as a dilution sink. Internal assumptions hold that downstream doses will stay within permissible limits. Epidemiological reconstructions now estimate that more than 30,000 to 124,000 residents in 39 riverside villages receive annual effective doses on the order of 0.1 to 1 sievert in 1950 through 1951, through ingestion and external exposure. To put that in context, 1 millisievert is approximately 0.1 rem. A chest X-ray delivers about 0.1 millisievert. The Teca residents are receiving doses hundreds of times higher. Exposure pathways are multiple: contaminated drinking water, irrigation of crops, consumption of fish, and external gamma radiation from contaminated sediments along the riverbanks. The absence of early individual dosimeters means that most residents have no idea of the doses they are accumulating. Early medical observations record blood, changes and other symptoms among riverside residents, later recognized as cases of chronic radiation syndrome. The Teca River Dosimetry System, TRDS, will eventually be developed as a retrospective reconstruction tool, using environmental measurements, diet surveys, and biological markers to estimate individual doses decades after the fact. But at the time, there is no in-field instrument capable of providing that information. A later IAEA scenario summary notes that Teca contamination resulted in chronic external and internal exposure of about 30,000 residents of riverside villages. Partial evacuations, water use bans, and upstream dams begin in 1953 and continue through 1956. These interventions reduce direct waterborne doses, but the core operational answer is not to minimize the inventory of high-level waste. It is to divert the highest activity waste away from the river and into underground tanks that will depend on continuous cooling. The Teca episode proves that waste can deliver sievert-scale doses to civilians. The institutional response is to concentrate it in buried steel vessels. By 1956, waterborne discharges to the Teca are officially curtailed. The highest activity waste now flows into underground storage, where its heat must be removed, and where failures will be much harder for villagers to see. Construction drawings specify a concrete canyon 8.2 meters deep, lined with stainless steel cans and capped by massive slabs. Each tank is designed to hold tens of tons of high-level liquid waste, surrounded by a water-filled cooling jacket. The year is 1951 to 1953. The tank farm is under construction at Mayak. Officially, the tank farm is a solution. High-activity raffinate is removed from the Teca and placed in engineered storage with active cooling and shielding. The design centers on preventing uncontrolled releases and providing radiation shielding for workers. But instrumentation is sparse. There are no robust independent temperature probes inside the waste volume and limited verification of cooling coil integrity. The waste itself is raffinate from the sodium uranyl acetate reprocessing process. Irradiated uranium fuel is dissolved in nitric acid. The oxidation state is adjusted. Uranium and plutonium are precipitated as acetates. Plutonium is separated for weapons production, and the remaining high-level waste containing fission products, actinides, and large quantities of sodium nitrate and sodium acetate is sent to the tank farm. A later technical summary estimates that the doomed tank held approximately 70 to 80 tons of liquid waste, generating about 79 kilowatts of decay heat. The waste composition is primarily sodium nitrate and sodium acetate, both of which are chemically stable when dissolved in water, but can decompose exothermically if dried and heated. The design assumes that water cooling will run indefinitely and that maintenance will detect any failure early. No dedicated safety system asks the more basic question: what happens if a cooling coil fails and no one notices for months? On paper, the tank farm provides shielding and active cooling. In practice, it creates large, poorly monitored inventories of chemically unstable waste whose safe state depends on a single cooling loop and the assumption that deviations will be noticed. A later technical review notes that, The tank held liquid radioactive wastes that required decay heat cooling to remove about 79 kilowatts. By the early 1950s, the TECA's dose curve bends downward. In the tank canyon, a different curve, waste temperature versus cooling reliability, has not yet been drawn. The strategic priorities assume that any environmental or waste management shortcomings are temporary costs on the path to weapons parity. In practice, this under-design of waste systems becomes the structural reason a single tank failure can later affect hundreds of thousands of people. Maintenance records show declining flow rates and repeated minor faults in one tank's cooling circuit. The years are 1955 to early 1957. At some point, the cooling loop fails outright and is not repaired. Internal reviews later acknowledge that the system was left inoperative for a considerable period of time. Technological regulations mandated prompt restoration of cooling and continuous monitoring. In practice, the tank remained in service as if its cooling coil were functioning, because external indicators, ambient dose rates and general coolant headers, appeared normal. Later reconstructions point to plausible failure mechanisms documented in technical literature: corrosion of cooling coils, deposition of salts inside pipes, valve malfunctions, and blockages that are never fully corrected. The Encyclopaedia Britannica's summary is succinct. Failure to repair a malfunctioning cooling system in a buried tank where liquid reactor waste was stored. For more than a year, the tank's contents grew steadily hotter. Operating culture, under production pressure, treats the tank as available storage, even when its cooling status is uncertain. The regulations assumed coil failures would be transient. The actual operating practice allowed a non-functioning cooling loop to persist, turning an engineering fault into a long-term thermodynamic experiment. By mid-1957, the tank is no longer being adequately cooled, leaving decay heat, tens of kilowatts, essentially unremoved. The absence of direct tank-by-tank temperature and pressure monitoring converts a repairable equipment failure into an undetected change of state. On paper, the tank farm still meets design assumptions. In reality, one vessel is now operating with 79 kilowatts of heat and effectively no engineered heat sink. One reconstruction summarizes the chain as technical failures coupled with violation of the tank cooling regime. By early 1957, the plant's paperwork still lists the tank as standard high-level liquid storage. In thermal terms, it has started the slow transition toward a large buried chemical charge. The tank's contents are entering a regime that no operating procedure anticipated, a regime where water gradually boils off, salts concentrate, and the waste transitions from a liquid to a solid, reactive mass. Physico-chemical models constructed decades later simulate a closed volume in which nitrate and acetate salts dry, compact, and heat in the absence of convective cooling. The waste is treated administratively as liquid, high-level waste. By mid-1957, much of it is no longer liquid. As cooling ceases, the waste warms, water gradually boils off, nitrate and acetate salts become increasingly concentrated. Temperatures reach approximately 350 degrees Celsius. Water has largely evaporated, and decomposing ammonium nitrate and organics are accumulating gases and energy. The waste storage system, intended as a passive sink, becomes an active hazard as its state shifts from cooled liquid to hot, porous, reactive solid, a state the plant had no instrumentation or operating procedures to track. Exothermic decomposition of nitrate and acetate mixtures produces gases and heat. Internal pressure builds. The transition from solvated ions to a chemically active solid mass is complete. The Environment and Society portal notes that the waste started to heat up, eventually exploding at a temperature of 350 degrees Celsius. The 160-ton concrete cover burst. No design basis accident had considered extensive drying and subsequent exothermic decomposition of the solids. Measurable neutron or power excursions are not reported. This is not a nuclear criticality. What began as decay heat management becomes a classic process safety failure, a large inventory of energetic material confined in a poorly instrumented, structurally strong vessel. The waste is closer in behavior to an overheated chemical reactor than to the stable waste repository envisaged in the design documents. By late summer 1957, the tank's contents are undergoing a chemical transformation that no one is monitoring. the design centered on preventing nuclear excursions, the accident will instead emerge from a neglected chemical pathway. Nevertheless, the radiological consequences will rival those of a major reactor release because of the tank's inventory. For operators, the tank remains a line on a log sheet. In thermodynamic terms, it has become one of the largest buried chemical charges in the Soviet Union. A panel of analog meters tracks coolant flows, general radiation fields, and power outputs. None directly display the actual temperature profile inside the failed tank. The years are 1956 to 1957, the control and dosimetry, rooms at Mayak. Plant documentation describes systematic control of waste storage, but later reviews admit that the only consistent indicators were external radiation fields and periodic sampling, not real-time measurements of internal conditions. The plant's internal safety chain includes shift supervisors, radiological protection services, and the ministry's technical inspectorate. They rely on aggregate indicators such as average dose to workers or area monitors. Control panels display system-level parameters, flow in common cooling manifolds, area dose rates, equipment status, but not individual tank temperatures or pressures. Official accident investigations later note that no direct continuous measurement of the failed tank's internal temperature existed. Radiological safety staff rely on external radiation fields and periodic sampling as their primary indicators. On paper, systematic control existed. In practice, the monitoring architecture could not detect the specific failure mode unfolding in one tank. The absence of an alarm was taken as proof of safety until the day the concrete lid moved. Because no one system reported the actual heat balance in each tank, the absence of alarms was interpreted as evidence of safety. The monitoring architecture itself becomes a cause. It structurally favors confirmation rather than detection of outliers. In a memo to the CPSU Central Committee, Minister E.P. Slavsky names the head of the radiochemical plant and the chief engineer, who committed a gross violation of the technological regulations for the operation of storage of radioactive solutions. The ministerial order notes that insufficient cooling allowed the container to increase in temperature to the point its contents reacted with each other and exploded. In the Commission's final wording, a single phrase, gross violation of technological regulations, becomes the official shorthand for what was, in reality, a structural blind spot in how Mayak measured waste behavior. On the morning of the 29th of September, all visible instruments suggest that the underground waste inventory is stable. The uninstrumented chemistry disagrees. At 16 hours, 22 minutes local time, 11 hours, 22 minutes UTC, one of 14 stainless steel containers in the canyon detonates. The date is the 29th of September 1957. The concrete cover, 0.8 meters thick, weighing approximately 160 tons, is thrown aside. A brick wall 200 meters away is damaged. No criticality accident occurs. The reactors continue to operate. The event is strictly chemical, yet the radiological source term is comparable to a major reactor release. At some point before 1622, internal pressure and temperature surpass the mechanical limits of the dried salt mass and tank structure. Then, a chemical explosion occurs, breaching the tank and overcoming the structural resistance of the concrete cover. The explosion energy, estimated at 70 to 100 tons of TNT equivalent, comes from rapid decomposition of dried salt, not from fission power. About 740 petabecquerels, 20 million curies, of radionuclides are mobilized, approximately 90% deposit on or near the site, approximately 10%, 74 petabecquerels, 2 million curies, are lofted and carried away by wind. Contemporary descriptions recall a column of smoke and dust that rose to a kilometre high. The dust flickered with an orange-red light. Wikipedia's summary is precise. The explosion completely destroyed one of the containers out of 14 total containers in the canyon. The initial radionuclide vector includes short-lived isotopes plus longer-lived strontium-90 and cesium-137 that will define long-term dose. The failure to repair one cooling system converts a single-tank abnormal condition into a regional contamination event. By design, The waste inventory per tank is large enough that any breach is inherently major. As the working day ends, a tank that was never supposed to change state acts like an unacknowledged reactor. It releases its entire energy potential in a single, uninstrumented instant. Within minutes of the blast, perimeter instruments finally report the information the tank never did. Dose rates that force the plant to admit an accident has occurred. The design centered on preventing nuclear excursions. The accident instead emerges from a neglected chemical pathway. Nevertheless, the radiological consequences rival those of a major reactor release because of the tank's inventory. Internal alarm circuits activate, and radiological teams begin surveying buildings, roads, and transport inside the site. A decision is taken to keep reactors online while decontamination starts. The evening of the 29th of September through the early 30th, at Mayak and Chelyabinsk 40. Emergency planning documents had assumed localized leaks or fires. The site now faces broad contamination of an active weapons complex. Yet external communication remains tightly controlled. The surrounding population receives no immediate warning. On-site dosimetry teams deploy, measuring elevated dose rates on roads, buildings, and vehicles. Decontamination begins, washing of surfaces, movement restrictions, first internal cordons, hosing and removal of contaminated topsoil, control of internal traffic, and protection of key reactor and radiochemical buildings. Preliminary dose rate mapping on the plant territory, and first attempts to estimate the release term. One summary describes that a plume containing 2 million curies, 80 petabecquerels of radionuclides, spread out over hundreds of kilometers, with the rest depositing near the site. About 90% of the 740 petabecquerels deposits on or near the industrial site, compounding existing contamination in the Tesha system and around Lake Karachay. Emergency measures focus on preserving continuity of weapons production and protecting the closed city itself, which had been intentionally sited upwind. Minimal attention is paid in this first phase to the still unknown downwind population. An IChemE review summarizes the situation succinctly. Large quantities of radioactive material were released, affecting an area of around 20,000 square kilometers, home to approximately 270,000 people. The choice to treat the event as a classified internal emergency, rather than a public radiological accident, shapes all subsequent decisions about notification and evacuation. Within hours, Mayak has partial contamination maps for its own territory. The plant still has no measured data on where the 2 million curies airborne plume will fall. While contamination maps begin to appear on desks in Chelyabinsk 40, the only visible sign outside the fence is an unusual glow in the evening sky. Meteorological data from that day, later reconstructed, show winds carrying the cloud to the northeast for approximately 10 to 11 hours after the explosion. The dates are the 29th through 30th of September, 1957, the downwind corridor northeast of Mayak. Planners had not modelled long-range dispersion from a tank explosion. In practice, fallout extends over 8,000 to 20,000 square kilometers, creating what will be named the East Ural Radioactive Trace, ERT, a zone roughly 300 to 350 kilometers long and up to 50 kilometers wide. The initial contamination levels in the central EURT show surface strontium-90 above 3.7 to 4 kilobecquerels per square meter, approximately 0.1 microcurie per square meter, in core areas, with cesium-137 and other fission products contributing to external dose. Approximately 15,000 to 20,000 square kilometers receive contamination higher than 3.7 kilobecquerels per square meter of strontium-90. Approximately 1,000 square kilometers become known as the East Ural's radioactive trace. Around 270 to 273,000 people live within the contaminated area at the time of the accident. The combination of high release height, stable atmospheric conditions, and harvested fields, with minimal ground interception by crops, maximizes ground deposition on inhabited areas. The same state that avoids public discussion of Kyshtym invests in decades-long environmental and biological research programs within the trace. One environmental history notes that the 20 million curies settled over an area of 20,000 square kilometers, home to 270,000 people. Originally, no planning scenarios anticipated tank failure as a source for a long-range plume, yet the EURT's geometry is now defined primarily by the combination of release height, meteorology, and the absence of vegetation on harvested fields. Regional meteorological logs for that Sunday record routine wind and cloud observations. They do not mention that the same air mass is now carrying the largest waste release in Soviet history. Even as the EURT is taking shape on the ground, the term itself will not appear in public literature for more than a decade. For the people living under it, there is no official name for what has just altered their land. In villages downwind, residents later recall unusual dust and sky glows. Local newspapers describe northern lights in the South Urals. In several rural districts, eyewitnesses later recall red dust settling on roofs and fields, and the Teka's water turning black for days. The dates are October 1957 through 1959. 22 evacuated settlements within the EURT. Evacuation of approximately 10,000 to 12,000 residents from at least 22 settlements begins on the 6th of October 1957 and continues in phases until 1959. Officials provide vague instructions: slaughter livestock, bury crops, but rarely mention radiation explicitly. Peasants in the path of the trace know the plant is dangerous. They do not yet know their approximate dose. Stores close, food is shipped in, and houses in evacuated villages are burned or demolished to prevent return. Evacuation patterns vary: populations, days until evacuation, and mean effective doses. For example, Berdianish receives 520 millisieverts, Ruskaya Karabolka 440 millisieverts, Alabuga 120 millisieverts. Retrospective dose estimates for the most contaminated evacuated villages show group mean effective doses in the range 120 to 520 millisieverts, 12 to 52 rem, and red bone marrow doses up to roughly 570 milligray, approximately 0.57 gray, in the closest 3 settlements. To provide a benchmark, 1 millisievert is approximately 0.1 rem, on the order of a year of natural background in some countries. A chest X-ray delivers approximately 0.1 millisievert. The Teka residents and EURT evacuees are receiving doses hundreds to thousands of times higher. Lack of immediate information and partial, staged evacuations lead to heterogeneous doses. Some families leave after days, others remain for months, and ingestion pathways, milk, vegetables, continue even as external dose rates decline. Early clinical observations include nausea, skin injuries, blood changes, and later identification of chronic radiation syndrome in the region. Chronic radiation syndrome is primarily known from the Kyshtym disaster, where 66 cases were diagnosed. Aklayev's review notes that the EURT cohort alone comprises approximately 21,400 people, embedded in a larger exposed population. The state organizes evacuations and bans on produce, but official explanations remain vague. People are moved, livestock slaughtered, and crops destroyed for sanitary reasons, while individual dose information is withheld. In medical statistics compiled years later, 66 cases of chronic radiation syndrome appear as coded diagnoses. In the original discharge summaries, most are described simply as residents of contaminated territories. Years later, when dose reconstruction tables assign specific sievert values to these villages, they will quantify exposures that, at the time, were experienced simply as unexplained orders to leave homes and fields. Teams from Mayak's Health Physics Department, Regional Civil Defense, and the military drive transects along the fallout path, stopping at fixed intervals to measure dose rates and collect soil cores. The dates are late 1957 through 1960. Ozyorsk, regional command posts and field survey teams. Military and civilian radiation survey teams trace the plume's path by driving transects and taking soil and dose rate measurements, producing hand-drawn isodose maps that will later underpin the EURT designation. Survey teams classify areas by surface contamination and dose rate thresholds. Cordons and signage are placed. This data later feeds into dosimetry systems such as TRDS 2016MC. The methodology includes vehicle-mounted and portable dose rate meters, soil sampling for strontium-90 and cesium-137, compilation of isodose maps that delineate zones for evacuation, restricted use, and conditional habitation. This work feeds into internal designations and classifications of EURT zones. Officially, the zone is treated as a restricted special regime area. Externally, there is still no acknowledgement that a large-scale radiological accident has occurred. The CIA will piece together the basic pattern by 1960 from aerial reconnaissance and informants, but withhold the information from the public for decades. CIA documents, later released, show that the United States had intelligence about a radiological incident near Kyshtym by 1959, but chose not to publicize details. A Western technical review decades later will summarize the entire process. The 1957 accident contaminated a larger area with the highest exposure levels in an area that is called the East Ural Radioactive Trace, EURT. The decision to classify nearly all accident data ensures that only limited information reaches affected communities, but it also produces unusually rich internal data sets for later epidemiology, once they are declassified. Internally, the state uses extensive surveying and mapping to manage the consequences. Externally, it maintains silence. This dual approach both restricts local knowledge and creates one of the most data-rich chronic exposure field laboratories in radiation epidemiology. Yunsier later describes the contaminated area as the East Urals Radiation Trace, EURT. About 273,000 people lived in the contaminated area. By 1960, 3 separate institutions, the Mayak plant, the Soviet security apparatus, and the CIA possess detailed maps of the trace. Only the residents living within it do not. By 1960, 3 institutions, the Mayak operator, Soviet security organs, and the CIA, possess detailed internal maps of the trace. The residents who live within its contours do not. Bulldozers push contaminated topsoil into fenced enclosures, later referred to as graveyards of the earth. The dates are 1957 through 1968. The EURT zone and administrative centers, Chelyabinsk Oblast. Official narratives stress routine, resettlement, and agricultural reorganization. In reality, approximately 10,000 to 12,000 people are removed from at least 22 settlements over about 2 years, while a much larger population remains in contaminated territories with varying restrictions. Around 270,000 remain in various levels of contamination, with a collective effective dose of several thousand person-sieverts. In 1968, the state establishes the East Ural Nature Reserve, Zapovednik, over the most contaminated part of the trace, formerly for ecological research, functionally a long-term exclusion zone. Access is tightly controlled, enabling scientific monitoring while keeping public attention low. A description of the reserve notes that it serves for long-term scientific study of the effects of radiation on the forest steppe ecology. Official descriptions state that the reserve is intended for long-term scientific study of the effects of radiation on the forest steppe ecology. Concealment of the accident in public discourse coexists with intensive scientific monitoring inside the reserve, producing data that will later underpin radiation protection standards far beyond the Urals. The same state that avoids public discussion of Kyshtym invests in decades-long environmental and biological research programs within the reserve. Lessons drawn will influence radiation protection standards internationally. On maps published for general circulation, the EURT becomes simply a green patch labelled Strict Nature Reserve. Only in restricted reports does it remain a radiological contour plot. On regional maps, the EURT becomes a green patch labelled Strict Nature Reserve. In internal tables, it remains defined by columns of becquerels per square metre and millisieverts per year. In 1976, Zhores Medvedev publishes an article in New Scientist describing a nuclear disaster in the Urals. In 1979, his book elaborates the claim. The dates are 1976 through present, London, Moscow, Ozyorsk, and the international research community. Western experts initially debate whether such an accident could have occurred without notice. Westerny press had carried vague reports of a catastrophic accident as early as 1958 through 1959, but details remained scarce until Medvedev's work and post-Chernobyl Soviet disclosures. After 1989, Soviet and then Russian authorities released data, enabling more rigorous dose and risk analysis. Aklayev's 2017 overview presents the core numbers. Kyshtym released 20 million curies, 740 petabecquerels, with 2 million curies, 74 petabecquerels, forming the EURT. Key results include 66 diagnosed cases of chronic radiation syndrome among the most exposed populations, estimates of approximately 49 to 55 excess cancer deaths among Riverside residents attributable to combined TECA and EURT exposures. TRDS 2016D and related systems now provide individual dose estimates for tens of thousands of people, underpinning research on chronic low-dose rate risk. Situate Kyshtym among high-magnitude civilian nuclear events, INS level 6 and above, alongside Chernobyl and Fukushima, while emphasizing its unique character as a waste tank accident, producing long-term mixed internal-external exposures. Early speculation suggests thousands of deaths. As Soviet and then Russian scientists release cohort data, the picture becomes more constrained, but still grave. 66 diagnosed cases of chronic radiation syndrome linked to the accident and its precursors, elevated solid cancer risks in TECA and EORT cohorts, and an estimated several dozen to low hundreds of excess cancer deaths attributable to combined exposures. TRDS 2016MC and related dosimetry systems reconstruct internal and external doses using Monte Carlo methods. These dose histories feed into risk models that remain central to low-dose rate radiation protection debates. Kyshtym joins Chernobyl and Fukushima as one of the 3 highest magnitude civilian nuclear events, INS 6 and above, but its specific legacy lies in chronic mixed exposure from waste rather than reactors. It becomes a core reference case for waste tank safety, emergency planning, and the ethics of secrecy in nuclear operations. The minister's confidential verdict that plant leaders had committed a gross violation of the technological regulations remains the most concise summary of the accident's root cause. The decades of dosimetry and epidemiology that followed quantify, in sieverts and becquerels, the long tail of that single administrative phrase. A single uncorrected cooling failure in 1957 becomes, over decades, one of the cornerstone case studies in waste safety, low-dose epidemiology, and the ethics of secrecy in nuclear operations. The ministerial phrase, gross violation of technological regulations, remains the official root cause summary. The sieverts, becquerels, and excess cancers documented since then quantify, in numerical form, how far the consequences of that single administrative failure extended beyond the concrete canyon at Mayak. If you value nuclear history told with documents, measurements, and long-term data rather than speculation, consider subscribing or supporting the channel so more of these declassified incident records can be turned into accessible, evidence-based documentaries.